Hi, welcome to the next video. So the last lesson we ended with the arc length formula theorem, and so I'm just going to open this class with the theorem again. So the arc length formula. Okay, so we concluded this theorem at the end of last class. If f prime is continuous on the finite closed interval a comma b, then the length of the curve y equals f of x from a less equal to x less equal to b is capital L, which is equal to the definite integral from a to b of the square root of 1 plus f prime of x squared dx, or capital L is equal to the definite integral from a to b of the square root of 1 plus dy dx squared dx. Okay, so that's the arc length formula theorem. Okay, and so now in this next example, we will use that theorem. So you get the solution. Example, find the length of the curve of the arc of the semi-cubical parabola y squared equals x cubed between the points 1, 1 and 4, 8. Okay, so we're going to find the length of the arc of the semi-cubical parabola y squared equals x cubed between the point 1, 1 and the point 4, 8. Okay, and so you can use your graphing calculator to graph this. And so to do that, okay, you graph it. It goes there. That's the graph of those two points on it. This is the graph of the curve y squared equals x cubed. Okay, and so we're going to find the length of the arc between these 2 points, the length of the arc right there. Okay, and so to do that, we will use the arc length formula right here. We're going to use that equation. Okay. So the length L is equal to, I'm going to write solution here. Okay, so the length L of this arc is equal to the definite integral from 1 to 4 of the square root of 1 plus f prime of x squared dx. Okay, and so let's find f prime of x. I'm going to erase the arc length formula theorem here. I have the equation, I wrote it down here. Our f prime is continuous in this example, so we can use it. It's continuous on that interval, so we can use this. Okay. Okay. So our graph is our curve is y squared equals x cubed. That's y equals x to the 3 halves. Okay, so finding y explicitly in terms of x, y is equal to x to the 3 halves. And so f prime of x is dy dx. That's the derivative of that, which is 3 halves x to the 1 half. Okay, so dy dx is 3 halves x to the 1 half. And f prime of x squared is equal to 3/2 x to the 1/2 squared, which is 9/4 x. Okay, so f prime of x squared is 9/4 x. This is equal to differential from 1 to 4 of the square root of 1 plus 9/4 x dx. Okay, so let u be 1 plus 9/4 x. So we're going to use u substitution here. So u is going to be 1 plus 9/4 x. Du is equal to 9/4 dx. Okay, so to use u substitution, I can plug in what's in the square root for u right there. But what I'm missing is a 9/4 here. So to fix that, I'm going to put a 9/4 where it needs to be. It's going to be put here. Okay, so you put the 9/4 there, and multiply the inside by 9/4. That's 4/9. Inside by 9/4 and the outside by 4/9. You're multiplied by 1. You're not changing the value of the integral. Okay, so this is equal to 4/9. So 9/4 dx is du. So we have du, and then what's in the square root is u. It's now because of u substitution, you have that here. So this is by u substitution, by substitution rule for definite integrals. Okay. But now, what are the values of u for those corresponding values of x? When x is 1, you have 1 plus 9/4, which is 13/4. And so 13/4 goes there. When x is 4, then 9/4 times 4 is 9. 9 plus 1 is 10. And so then u is 10. And the 10 goes there. Okay. So by the substitution rule for definite integrals, that definite integral equals that one. Okay, and so now 4/9, this is equal to 4/9 times, now an antiderivative of u to 1/2 is 2/3 u to the 3/2, evaluated from 13/4 to 10. And this is equal to, well, 4/9 times 2/3, that's 8/27. Okay, and so 10 to the 3/2 minus 13/4 to the 3/2. Okay, and that looks a little weird, but you can just calculate that. You can put in your calculator, and when you put that in your calculator, you get, okay, well, never mind, let's not put it in your calculator. Let's just leave it like that. And you can simplify this with some work as 1/27 times 80 times root 10 minus 13 times root 13, if you like that more. All right, so there's the answer. And that is the answer to that example. Okay, so now we've applied the arc length formula to finding the length of a curve. All right, so let's keep going. Okay, so let's keep going. So that's one example. Now let's talk about the arc length function. Okay, so it's called the arc length function. Okay, so if a smooth curve, capital C, has the equation y equals f of x, a less than or equal to x less than or equal to b, let s of x be the distance be the distance along capital C from the initial point P naught of A comma f of A to the point Q x comma f of x. Then S is a function called the arc length function, and S of x is equal to the definite integral from a to x of the square root of 1 plus f prime of t squared dt. Okay, so if a smooth curve capital C has the equation y equals f of x, a less equal x less equal to b, s of x be the distance along C from the initial point P naught to the point Q. Then S is a function called the arc length function, and S of x is equal to that. Okay, so to illustrate this, so let's say there's a picture illustration. I don't know why I'm labeling it, but I am. Okay, so picture illustration. The idea is this. So I'm just going to draw a curve here. Okay, here's a curve. So this is a smooth curved capital C, which the equation y equals f of x. From A to B, x equals A to x equals B. Excuse me, sorry. Let S of x be the distance along C from the initial point P naught, which is at A comma f of A. This is P naught. So we're going Q f x comma f of x. Let's say Q is here. Here's Q at x comma f of x. S of x, S is a function called the arc length function. S of x is equal to the definite integral from A to x of that. That will be the length of the arc starting at P naught along this curve of f, starting at P naught and ending at Q. So the length of that curve is S of x. And so that's S of x. The length of that curve there that I drew a little bit darker there. If I moved x, right, then I'd be moving the point on the curve that I stopped at. And then it would be the length of the curve from P naught to that point, other point on the curve with the x coordinate, that x. Make sense? Okay, so that's what the arc length function is doing. You just, as an input to the function, you're deciding where the x value, the point on the curve that you're stopping, which is the end point. And for some fixed point at A, comma f of A on the function, point P naught, where it's A, comma f of A. Okay? Okay, so that is the purpose of the arc length function. So if you read it like this, it can be a little bit hard to understand. If you see a picture of it, I think it's very easy to see what it's doing, right, from the picture. Okay, let's keep going. Okay, so ds dx, where s is that function I already wrote down, s of x is the definite integral from a to x of the square root of 1 plus f prime of t squared dt. That's s of x. ds dx is equal to the square root of 1 plus f prime of x squared. And that's equal to the square root of 1 plus dy dx squared. Okay, good. So ds So ds is equal to the square root of 1 plus dy dx squared dx. And what that implies is that ds squared is equal to this squared, which ends up being 1 plus dy dx squared times dx squared. When you multiply that out, you get dx squared plus dy squared. This is called symmetric form. Okay, so that's symmetric form. Okay, now if you draw a graph to illustrate what this is, kind of what this is meaning, let's switch the markers here. Okay, so here's x, here's y, there's the origin. If you have a curve like that, you have a point on the curve, let's say here, and let's say you have the tangent to the curve there. You have your right triangle here. Pictures much better. Okay, dx is the length of that leg of the right triangle. Dy is the length of that leg. ds is the length of the hypotenuse. And then delta y is the actual change in height from the starting point to that point. That's delta y. And delta s is the length of the arc on the curve, the length of there. Okay, and that's illustrating what's meant by dx, dy, ds, delta s, and dy. Okay, so the change in x, that's dx. So you take the tangent line, right? You take the tangent line, and you look at traveling along the tangent line. Then the change in x is dx, the change in y in the tangent line is dy. But now, instead of going along the tangent line, if you think of going along the curve itself, delta s is the length of the arc that you traveled. ds is the length of the tangent line. Delta y is the change in y values along the arc. Okay? That's illustrating what all those things mean in a picture. Okay. L is equal to the integral of ds. Okay, and ds is equal to the square root of 1 plus f prime of x squared dx. It does, but we can also write it this way. It's equal to 1 plus dx dy squared dy. Okay? All right, so that's that. And I need to get another marker. Okay, back. So let's do another example. Example. Find the arc length function for the curve y equals x squared minus 1/8 ln x, taking p naught 1, 1 as a starting point. Okay, so find the arc length function for the curve y equals x squared minus 1/8 ln x, taking p naught 1, 1 as the starting point. Okay, so let's do that. Solution. So let f of x equal x squared minus 1/8 ln x. Okay, what we want to do is we want to calculate the definite integral from 1 to x of the square root of 1 plus f prime of t squared dt. T is the dummy variable. So to do that, we need the derivative of the function to plug in here. So f prime of x is equal to 2x minus 1/8 times 1 over x. Okay, and so now I can plug that in for f prime there. And so this is equal to the differential from 1 to x of the square root of 1 plus that squared. That's x to the minus 1, so this is t to negative 1 squared dt. So that's 1 plus this squared, which is 4t squared. And then you FOIL this out. So if you do 2t minus 1/8 t to the minus 1 times 2t minus 1/8 t to the minus 1, that's equal to this times this, which is 4t squared minus 1/4 minus 1/4 plus 1 over 64 t to the negative 2. Okay? And so you combine the minus 1/4 and minus 1/4 to get minus 1/2. So here you get you get 4t squared plus 4t squared minus 1/2 plus 1 over 64 t to the negative 2. That's dt. And this is equal to differential from 1 to x of the square root 4t squared plus 1 over 64 t negative 2 plus 1/2 dt. Okay, and so this is equal to differential from 1 to x of the square root of, and now how do you express that? Okay, 2t plus 1/8 to t to negative 1 squared. That's dt. So if you take 2t plus 1 over 8t to negative 1, you square it, you get that circled part. And so let me justify that here, where I did these calculations. Okay, so if you take this thing and you square it, 2t plus 2t to negative 1 squared is equal to 2t plus 2t to negative 1 times 2t plus 2t to negative 1. And if you multiply, 2t plus 1/8 plus 1/8 t to negative 1 plus 1/8 t negative 1 plus 1/8 t to negative 1. So if you multiply that out, you get 2t times 2t, which is 4t squared. 2t plus 1/8 t to negative 1. 2 times 1/8 is 1/4, and the t and t minus 1 cancel. And you get plus 1/4. And then this times this, you get 1/8 times 2, which is 1/4, and the t and t minus 1 cancel, so it's plus 1/4. And then this times this is plus 1 over 64 t to negative 2. And so when you combine, you get that this squared, that squared is equal to 4t squared plus 1/2 plus 1 over 64 t to negative 2. Okay, so 4t squared plus 1/2 plus 1 over 64 t to negative 2 is 2t plus 1 over 8 t to negative 1 squared. So I just substitute this for that. Okay, so what's inside the square root instead of being this is now that. Now since I express this as something squared, when you take the square root of it, the square root and the square cancel. And you're left with just the one expression, differential from 1 to x of 2t plus 1/8 t to the negative 1 dt. Okay, so you find the differential of that, calculate that differential. What's an antiderivative of the integrand? It's t squared plus 1/8 ln t. And so you evaluate that antiderivative from 1 to x. And when you do that, you get x squared plus 1/8 ln x minus 1 squared plus 1/8 ln 1. ln 1 is 0, so you're just left with minus 1 squared, or minus 1. That's minus 1. That's the final answer. That's s of x. You get x squared plus 1/8 ln x minus 1. And that is the final answer. Okay? So find the arc length function. We want to find the arc length function for the curve y with p naught as the starting point. That this is s of x here. Okay? So that's s of x. S of x equal to that, which is that. And so we found the arc length function. The arc length function is this guy, s of x. Right, so now here's an example of finding the arc length function in a problem. Okay, and that's the end of 7.4. Okay, let's keep going. All right, so that's 7.4, so next is 7.7. So 7.7 is differential equations. All right, so this is the last section in the course. Well, for this chapter, okay? Okay, so a differential equation is an equation that contains an unknown function and one or more of its derivatives. And see, here are some examples. First example is y prime equals xy. So the definition of a differential equation is that a differential equation is an equation that contains an unknown function and one or more of its derivatives. So this contains the function y and one of its derivatives y prime. Okay, and so that is a differential equation. It meets the conditions for a differential equation. Okay, the second differential equation in this list is going to be y double prime plus 2y prime plus y equals 0. And so this is an equation that contains an unknown function and one or more of its derivatives. It contains the first derivative and second derivative. So that is also a differential equation. Here's the third example of a differential equation, d3y dx3 plus x d2y dx2 plus dy dx minus 2y. Okay, so the third differential equation is d3y dx3 plus x times d2y dx2 plus dy dx minus 2y equals e to the negative x. Okay, so that's the third differential equation. Okay, and so in the third, you also see y is an unknown function in the equation, and we have the first derivative, second derivative, and third derivative in that equation. Okay, and so differential equations are important because very oftentimes, one reason it's important, other than for the mathematical beauty of it, in application terms, a lot of times in science, when they need to describe a physical law or laws, they need differential equations to describe the nature of something. And so these have a lot of applications in science also, differential equations. Okay, keep going. The order of a differential equation is the order of the highest derivative that occurs in the equation. Okay, so thus on the last board, thus equations 1, 2, and 3 are of order 1, 2, 3, respectively. Okay, so for instance, the first equation is y prime equals xy. The second equation is y double prime plus 2y prime plus y equals 0. And the third equation is d3y dx3 plus x times d2y dx2 plus dy dx minus 2y equals e to negative x, right? Now, those are the three differential equations that were on the last board. And so this is order 1, because the highest derivative of the function is the first derivative. This is an order 2 differential equation, because the highest order of the derivative of y is the second derivative. And this is an order 3 differential equation, because the highest order of the derivative of y in this equation is the third. Okay? And so that's order 1, order 2, and order 3 differential equations. Okay, so that is the definition of the order of a differential equation. Okay. Okay, so let's keep going. A function f is a solution of a differential equation, if the equation is satisfied when y equals f of x and its derivatives are substituted into the equation. Okay, so thus f is a solution to y, to equation 1, if f prime of x is equal to x times f of x for all values x in some interval. Okay, to remind you what equation was equation 1 again was y prime equals xy. Okay, so y equals f of x is a solution. F is a solution to this equation when y equals f of x and its derivatives are substituted into the equation and it holds. So thus f is a solution to this equation if f prime of x is equal to x times f of x for all x in some interval. Okay, That's the definition of a solution of a differential equation. Okay, so note, when we are asked to solve a differential equation, we are expected to find all possible solutions of the equation. Okay? So there's not necessarily only one solution to a differential equation. There could be infinitely many solutions. And so you're expected to find an expression or a representation of all the possible solutions of a differential equation. Okay? So one more time, when you're asked to solve a differential equation, you're expected to find all possible solutions of that equation, which is oftentimes more than one. Okay? Okay, so that's the start to studying differential equations. Now, the differential equations are classified in different ways. They're separated into types of differential equations. And so one type of a differential equation is called a separable equation, a separable differential equation. And so these are pretty easy to solve. Okay, this is a good place to start when studying differential equations. So definition, a separable equation is a first order. Remember, a first order differential equation means the highest derivative of the function is the first derivative. So it's a first order differential equation that can be written in the form dy dx equals g of x times f of y. Okay, so a separable equation is a first order differential equation that can be written in the form dy dx equals g of x times f of y. And the word separable in the name is from the fact that you can separate the thing you set dy dx equal to into one expression of x times and a separate expression for y. And so the expression of x is completely separate from the expression of y. It's not mixed. It's an expression using only x times an expression using only y equals dy dx. Okay? So equivalently, if f of y is not equal to 0, we could write for dy dx is equal to g of x over h of y, where h of y is equal to 1 over f of y. Okay, so if f of y is never 0, then you could talk about its reciprocal, 1 over f of y. Now, why would you want to talk about 1 over f of y? Because if you take g of x and divide it by 1 over f of y, it's the same as multiplying by f of y. And so we could call the function h of y equal to 1 over f of y, and instead of multiplying by f of y, we could divide by h of y. And so we can say dy dx equals g of x over h of y. And so the reason why we would do this is because if we can have this equation where that equals that, we can solve it easier. So to solve this equation, we rewrite it in differential form. H of y dy equals g of x dx. Okay, so now here all the y's are on one side of the equation and all the x are on the other side of the equation. So that's why we write it that way, so we could do this. Okay, then we integrate both sides and get the integral of h of y dy is equal to the integral of g of x dx. So I'm going to call this equation 5, and I'm going to box it. Okay, so we now have this. Okay, so this defines y implicitly in terms of x, or as a function of x. And sometimes we can solve this equation explicitly for y in terms of x. Okay? Okay, so we end up with that. So we end up with this, and so there we go. So I'll leave this on the board for a moment so you can write this thing down. Okay. Okay, you would just integrate both these things, these functions, and you would get something equals something. One expression of y equals an expression of y equals an expression of x. That would be solving for y implicitly in terms of x. Okay. You could also solve, sometimes, not always, sometimes you can solve for y explicitly in terms of x. Y equals an expression of x, but not always. And you can say you have the answer without doing that. Okay, we'll see more of that later. So let me erase this. Okay, so usually we want to find a particular solution that satisfies some initial requirement. This is called an initial condition. Okay, so usually we want to find a particular solution that satisfies some initial requirement. This is called an initial condition. The problem of finding a solution of the differential equation that satisfies the initial condition is an initial value problem. It's called an initial value problem. Okay, so the problem of finding a solution of the differential equation that satisfies the initial condition is called an initial value problem. And so most of the times in differential equations, you can find a general solution of a differential equation, but you're oftentimes asked to find a particular solution that satisfies an initial requirement called the initial condition. Okay? It's called an initial value problem. Okay, so the next example we'll do, we will solve a differential equation and we'll find a particular solution that satisfies some given initial condition. okay? Okay, let's start with the next. The first example in the section 7.7. So example 1, part A, solve the differential equation dy dx is equal to x squared over y squared. So that's part A. Solve the differential equation dy dx equals x squared over y squared. Okay, solution. Okay, so we can just cross multiply. And so after cross multiplying, we get y squared dy is equal to x squared dx. Then we integrate both sides and get the integral of y squared dy is equal to the integral of x squared dx. Now this is equal to 1/3 y cubed is equal to 1/3 x cubed plus c. Each integral has its own plus some constant, but instead of adding an arbitrary constant to both sides, we can just add one constant to the right side, which would be really adding the difference of the two constants. Right, so if I added c1 here and c2 there, instead I could add a constant here that represents c2 minus c1. Okay, so here we have 1/3 y cubed equals 1/3 x cubed plus c. And now we have solved for y implicitly in terms of x. We solved for y implicitly in terms of x. Okay, so that's part A. Okay, so let's go to part B, where we're going to use the solution of that same differential equation. So I'm going to write, we can solve for y explicitly in terms of x, right? If we did that, we would have, first we have y cubed is equal to x cubed plus 3c, right? Which is then its own constant, which I can still call c. And if you take the cube root of this, you would get the cubed root of that. Okay, and so these two c's are not the same numbers, but they're just both constants. Right? So I can just write plus c for those places, okay? So this is solving for y explicitly in terms of x, and this is solving for y implicitly in terms of x. Okay, and they both are valid answers. They're both perfectly fine answers for solving a differential equation. Okay, so part B, now that we've solved it, part B is find the solution of the differential equation dy dx is equal to x squared over y squared. So find the solution of that differential equation that satisfies the initial condition y of 0 is equal to 2. Okay, solution to part B. Okay, so here we have our general solution. And we want to satisfy the initial condition y of 0 equals 2. So y is 2, you get 1/3 times 2 cubed is equal to 1/3 times 0 cubed plus c. X is 0 and y is 2. And that implies that 8/3 is equal to 0 plus c, which equals c. That implies c is 8/3. Okay, so the final answer is, so finding the solution of that differential equation that satisfies the initial condition is letting c equal 8/3. The c is equal to 8/3 is for this differential equation. So we get c is 8/3 there. We won't get the same constant here. If we solve explicitly for y, we get y equals y cubed is equal to x cubed plus 8. And then when we take the cubed root of that, we would get that. So that's the particular solution. That's the solution satisfying this initial condition, solving explicitly for y in terms of x. This is solving for y implicitly in terms of x. And so now we've solved part B in either way. These are both answers. Okay? And so that's the answer to part A and B of example 1. Okay, let's keep going. Example 2. Okay, example 2 is solve the differential equation. So solve the differential equation dy dx is equal to 6x squared over 2y plus cosine y. Solution. Okay, so the solution is we have again a separable differential equation, and so writing the equation in differential form and integrating both sides, we have that the integral of 2y plus cosine y dy is equal to integral of 6x squared dx. Okay, so writing the equation in differential form would be saying 2y plus cosine y dy is equal to 6x squared dx, and then integrating both sides, we would be integrating from. Okay, and so we get this from that, again, by writing the equation in differential form and integrating both sides. And so we now have that. Now let's take the antiderivative of both sides. We get y squared plus sine y is equal to 2x cubed plus c, where c is a constant. And that's the answer. Okay, solve the differential equation. We solve for y implicitly in terms of x as y squared plus sine y equals 2x cubed plus c, where c is any constant. Where c is a constant. Okay, and so we've now solved that differential equation also, that separable differential equation. All right, good. All right. Okay, so let's do another example. Example 3. Solve the equation y prime is equal to x squared y. Solution. Okay. So rewriting the differential equation using Leibniz notation, we get dy dx is equal to x squared y. Leibniz notation is when you instead of writing y prime or y double prime, you'd use dy dx or d2 y dx2, d3 y dx3, that notation. Okay, so we have the differential equation dy dx equals x squared y. Line it up, equal sign. Okay, so if y does not equal 0, then we can write that 1 over y dy is equal to x squared dx. Okay, and then we integrate both sides, and we get the integral of 1 over y dy is equal to the integral of x squared dx. The integral of this is ln of y, ln the absolute value of y, and that's equal to 1/3 x cubed, and then plus a c, which is the difference of the two constants we added to each side. Okay, so now we've solved for y implicitly in terms of x. Okay, and we can solve for y explicitly by doing this. The absolute value of y is equal to e to the ln of absolute value of y, which is equal to e to the 1/3 x cubed plus c, which is equal to e to the c, e to the 1/3 x cubed. Okay, so now we have that the absolute value of y is equal to e to the c times e to the 1/3 x cubed. And so that's the absolute value of y. So y is equal to plus or minus e to the c, e to the 1/3 x cubed. And so y is equal to plus or minus e to the c times e to the 1/3 x cubed. Okay, so now we've solved for y explicitly in terms of x. Okay, now we have that solution there. So I'm going to erase this stuff here. Okay, so if y equals 0, so y equals 0 is also a solution because if you plug in y equals 0, you just get 0 on both sides. So okay, so so the general solution is of the form y equals capital A times e to the x cubed over 3, where capital A is an arbitrary constant. Okay? Either A equals e to the c, A equals e to the, or A equals negative e to the c, because of this, plus or minus e to the c, or A equals 0. Okay, so this applies for when y is not 0. When y is 0, it would be 0. And so if you just put A equals 0 there, then that would give you y equals 0. Okay, so you can write the general solution for any y, including y equals 0 in this form. But then if y is 0, then A is 0. Okay, and so our final answer is this. This is the answer. The question was solve the equation y prime equals x squared y. The answer is the general solution is of the form y equals a capital A times e to the x cubed over 3, where capital A is an arbitrary constant, and either capital A will equal e to constant c, or A will equal e to the negative constant, or A will equal e to the negative e raised to a constant, or capital A will equal 0. Okay, and that's the answer to example 3. Okay? Okay, so that's the solution to that problem. Okay, one more example. Example 4. So example 4 is solve the equation dy dt is equal to ky. Okay, so we stated this differential equation in 5.5, and we talked about the law of natural growth or decay. This is a separable differential equation, and so we can solve for it using the methods of this section, and we'll get the answer that we used before. Okay, so right, so what you get is dy is equal to dy over y. That's usually how people write it. Dy over y is equal to k dt. Right, writing in differential form, and then integrating, you get the integral of dy over y is equal to integral k dt. The integral on the left side is ln of the absolute value of y equals the integral on the right side, kt squared over 2 plus a constant c. Oh, sorry, wait. It's just k. It's k dt there. Integral k dt. And so that's kt plus c. What's that? Because that tells you that the absolute value of y is equal to e to the kt plus c, which is equal to e to the c, e to the kt. Okay, and then y is equal to capital A, e to the kt. Okay, so y equals capital A, e to the kt, where capital A is equal to plus or minus e to the c, or a is equal to 0, is an arbitrary constant. Okay, so if the absolute value of y is equal to e to the c times e to the kt, then y is equal to capital A, e to the kt, where capital A is plus or minus e to the c, or capital A equals 0, right? Just like before, if y equals 0, then you can just say a is 0. Okay, so solving that equation, we get y equals capital A, e to the kt, where a is plus or minus c, plus or minus e to the c, or a is 0. And a is an arbitrary constant. And that's it. That's the solution to that differential equation. Okay, and so now we're done with 7.7. Okay, study and do.